and welcome. Today we'll start the chapter Rotational Mechanics. Now, this is considered as one of the most difficult topics in physics. But if you pay enough attention to the basics, you would find that it's not as difficult, but instead this is one of the most interesting topics in physics. And this chapter involves all that we have learned so far in mechanics. Right. So before we start our discussion on rotational mechanics, let's first understand what a rigid body is. So a rigid body is, as you understand, is a body which does not essentially change its shape, right? So in strict definition, rigid body is a body where the distance between any 2 points on the body would not change. So a rigid body is such that distance between any 2 points on the body do not change. That does not change. The distance does not change. So this means that a rigid body would be a body where the distance between any 2 points would not change. Take a simple example. Think of a box. Now, if you move this box, the distance between any 2 points would not change. But instead, if we have 2 boxes combined through a spring, then during their movement, you can see that the distance might change, right? So this arrangement is not a rigid body, but the previous example where we had a single box, this is the case of a perfect rigid body, right? So in a rigid body, since the distance would not change, let's see what the consequences of this assumption would be. So what I've drawn here is a perfectly rigid body. Now, I'll assume that this line that I've drawn is the line around which this body is rotating. Right. So now, first of all, to simplify our calculations, I'll assume that this rigid body is made up of a lot of smaller bodies. Right. Now, we have dealt with such situations before. If you want to take such a case, you have to take an infinitesimally small particle and then integrate over the entire body. But right now, I'm just viewing this body as a collection of bodies which have finite mass. Right. So if I do so, and I've given you that this body, say, rotates with an angular speed omega. I hope you remember angular speed and angular velocity. We read about this in circular motion. So it is given that this rigid body is spinning about this axis with an angular velocity omega. We wish to find the kinetic energy of this body. So, given is the situation that there is a rigid body of mass m spinning about an axis with a constant angular speed omega, and we wish to write the angular speed, the kinetic energy, So, the kinetic energy, we know that if we take any one body, like say this, let me call it Mi. So this is of this collection, this is one particle and I'm giving it a general index Mi. So I can assume that this body is made up of, say, n masses, M1, M2 till Mn, right? So I'm considering a general body and I'm giving it the index I. So the kinetic energy of this ith body, I know by definition, would be half into the mass, which is Mi, into its speed square. Let's call it speed Vi, and then this gives us the expression for kinetic energy for this single body, right? Right. So the total kinetic energy logically would be the sum of kinetic energy of all these bodies, right? So if this single rigid body is made up of 10 smaller bodies, then if you find kinetic energy of all of these 10 bodies and add them up, then you get the total kinetic energy for this rigid body, right? So same is the case here. The total kinetic energy would be the summation of all these kinetic energies, where this index varies from I to 1 to n, right? If we have n such bodies, right? So now it is given to you that this body is spinning with an angular velocity omega, right? So let me say that the perpendicular distance of this ith body from this axis about which it is spinning is Ri, right? So Ri is the distance from this axis of this ith particle of which we are assuming the body is made, right? So if Ri is the distance, I hope you can imagine this body would go in a circle of radius Ri. Look at this animation to understand this better. You see the axis of rotation, the entire body. Now, if I give it a spin, you can see that this point traces out a circle, and the radius of the circle is nothing but its distance from this axis, right? So now, since a circle is being formed, recall that we know that linear speed in case of circular motion is equal to radius times the angular speed, right? We have read this before in circular motion. V is the tangential speed, omega is the angular speed, and r is the radius, right? So if we use such a relation, we can write that the translational speed, the tangential speed Vi is equal to the radius Ri into omega, right? So we can write this expression for this ith particle. So this equation can be written as summation of I from 1 to n half into mi into Ri square omega square, right? So now in this expression you see that omega is a constant, right? So we can take omega out of the summation and we could write something like half can also be taken out because it's once again a constant. So you would have a term like half into summation of mi Ri square into omega square, right? So the total kinetic energy of this body when it spins is of the form half into the summation of mi square into omega square, right? So now let's come to the entire idea which we want to establish here. We are going to compare this expression to the original expression of linear motion. Kinetic energy we know is equal to half into m into v square. So we see a similarity in these two expressions, right? Because in this case you have an expression of half into a term into the square of angular speed, right? And in the linear case we have half into mass into the square of linear speed. So this half sees its analog, omega clearly sees its analog. This is linear speed, this is angular speed. So we could say that these two terms are also sort of an analog of each other, right? And this term hence is defined as moment of inertia. So we'll understand this better as we keep moving forward. You would see why we are defining this term. You could say that the summation of mi/ri square does exactly what mass does in linear motion. So whenever we'll talk about rotation, moment of inertia is what mass is to linear motion. And moment of inertia, it is generally denoted by the symbol I. It is given by summation of mi/ri square, where I varies from 1 to n if you have a collection of n particles. Right? Let me stress this again. You can write this only if you're dealing with a collection of particles, right? You've done this enough to know that if we have differentially small masses, then such a term would turn, the summation would become integration, and instead of mi, we would write dm, the differentially small mass, into r square. So this is what the term would look like if you were to integrate. We'll come back to this later. Right now, let's only focus our attention at this term where we are defining moment of inertia of a collection of particles, a summation of mi ri square. Now here, mi is clearly the mass, right? There's no confusion about this. Notice that Ri is the perpendicular distance from the axis. And this perpendicular distance from the axis is nothing but the radius of rotation, right? It automatically becomes the radius of rotation if you spin something. So in a rigid body, as we have discussed, distance between 2 points does not change. So if I take any 2 points, let's call them point A and point B, then if you think about it, distance between any 2 points will be measured by joining these 2 points by a straight line, right? So if I wish to measure the distance between points A and B, we'll have to join these 2 points A and B, right? So now, if the distance between A and B cannot change, that means the length of this line AB cannot change, right? So let's say at any given point in time, B has a speed VB at an angle theta 1 with this line, which is the line joining A and B, and A has a velocity VA, again making an angle of, let's say, theta 2 with the line joining these 2 points A and B. Now, if the distance cannot change, then that means that with respect to A, B cannot move on this line AB. So let me first break these velocities into components. So this VB can be broken into two components, one being VB cos of theta 1, which is along this line, and then VB sine of theta 1, which is perpendicular to this line. Then VA can again be broken down into two components. One is VA cos of theta 2, which is along this line, and then VA sine of theta 2, which is perpendicular to this line, right? So let me draw this line again. Say this is point A, this is the straight line, and this is point B. Then we saw that their components are such. So actually let's keep point B here and A at this end, consistent with our original notation. So B has velocity VB sine of theta 1 in this direction, and VB cos of theta 1 along this line. Similarly, A has velocity VA sine of theta 2 perpendicular to this line, and then it has velocity along this line, which is given by VA cos of theta 2, right? So now, if B cannot move with respect to A, this can happen only if there is no relative motion, right? And for no relative motion, they must have the same velocity along this line, right? Because only then B would find A as stationary, right? Because two cars moving in the same line with the same speed would always see each other as stationary. So first of all, if such is the case, we can conclude that VB cos of theta 1 must be equal to VA cos of theta 2, right? So in statement, we could say that velocity of, or rather the component of velocity, along the line joining any 2 points must be the same for any 2 points. Right? So, what we see from here is that if you have 2 points and if we join them through a line, then the component of velocity of both of these points along this line has to be the same, because only then can it be a rigid body. Right. Furthermore, what we see is that B will only see A moving in a direction perpendicular to the line. Right. And if you think about it, then velocity of A with respect to B. So if we are talking with respect to an observer who is standing at B, he would say that A is moving this side, and I hope you can figure it out. The observer on B would see A as moving in this direction with a speed, first of all his own speed, which is VA sine of theta 2, plus he'll add his own velocity to A after inverting the sign, right? So it gets added and becomes VB sine of theta 1. So B sees A as moving in this direction with this given velocity. Right? So what he basically sees is that A moves tangential, or rather perpendicular to the line joining B and A. And as we have said, he would never see A as coming towards him. So A can only ever move in a tangential direction. So I say a tangent because if you think about it, if the distance is maintained, A will basically trace out a circle with respect to B, right? Because if this distance is never changing, then what A essentially will trace out is a circle, right? So such is the idea, or this is exactly what we wanted to discuss. So if you take a body, let's say it rotates about its center, right? So it's rotating like this about its center. So let's say we have three observers, observer A who is at the center, observer B who is somewhere in the middle of this platform which is rotating, and then there's observer C who is standing on the edge of this, right? Let's take another observer, let's call him D, and this observer is on ground. Now, of all these observers, A and D would observe exactly the same things, but only slightly differently. Now, A would see that B is going in a circle of this radius around him, right? A would say that B is tracing out this path. For C, he would clearly see C moving along the circumference of the circle, right? And A clearly sees that D is stationary. Now, D also sees A as stationary. He also sees that B traces out the circle and C traces out the bigger one. So this is fairly obvious. Now, when we come to B, if the observer is at B, B would see A as tracing out a circle like this, with B being at the center. So B would find that he's at the center and A is tracing out a circle of the same radius with which A was seeing B as rotating, right? So the radius that A would have reported for B is the same radius that B would report for A, but A would find himself at the center of this rotation, and so would B, and so B would also claim that he's at the center and A is going about in the circle of the same radius. Same is the case with C. B would find that C is moving in this radius, in a circle of this radius, and he would see that he's moving in a circle like this one, right? So what basically happens is that every observer finds the rigid body is rotating about him as the center, right? So now the question is, what about the angular speed? If the original angular speed is omega, then would all these observers see the same angular speed? Well, the answer is yes. So every observer on a rigid body would find that the rigid body is rotating with himself at the center, but the angular speed that these observers observe will all be the same. So let's now see the same thing in an animation to understand this better. So you can once again see we have four observers, A at the center, B and C going in different radius, and D as stationary on the ground. Now what we are seeing right now is the observation of A or D. So now let's switch to the mode where B is observing this. Now you can see that B finds that A is going in a circle around him, and the radius remains the same as the radius with which A had seen B to be moving. Also, see that B finds that C is also rotating with him at the center. And the same is the case with the observer D. He even finds that the observer D is going in a circle. Right. So for all these rotations, the angular speed remains the same. For even the observer C, you would find that the rotation would change in the manner that C would think he's at the center, but the angular speeds will remain the same. So we understood that in a rigid body, the angular speed, and this angular speed is referred to as the spin angular velocity. So this would remain the same for all observers who are on the rigid body, right? So having understood this, let's get back to our discussion of moment of inertia. So we had seen the expression for moment of inertia as only for a collection of particles, that moment of inertia I is defined as summation of mi/ri square, where I varies from 1 to n if you have a collection of n particles, right? So now first of all, let's see what if we have a single particle. That is the case where, let's say this is the center and a particle of mass m is going in a circle of radius r. So if such is the case, then we could say that for this particle, now pay attention that like most of the cases we had discussed before, this mass m is a point mass. So a point mass when placed at a distance r from the center of rotation, its moment of inertia would simply be equal to mr square, right? Mass times the square of its radius. Now let's check if its kinetic energy turns out to be the same if we use our revised expression, that is of half I omega square, and if we use the previous expression of half mv square. Now I hope you paid attention that when we wrote this xi, the term of kinetic energy had become half into I into omega square. Now we are just discussing this briefly. We'll come to this in detail when we come to kinetic energy of particles. Then we'll once again go over this, how to write kinetic energy of particles, right? So in this case, let's say the particle is going with an angular velocity omega, has a translational speed v and the radius is given to be r. Now, if its translational speed is v, we know that kinetic energy is equal to half mv square, right? Now, looking at a new expression which says that kinetic energy is equal to half I omega square, we would get half into. Now, we just established that moment of inertia for a point mass would be mr square, right? So, half into mr square into omega square. Now, you can see that r square omega square can be clubbed together and we can write it as r omega the whole square. Now, r omega is nothing but v, so these two expressions are exactly the same. So this, and there are a lot of applications which will help you understand the significance of moment of inertia. But first of all, we'll focus our attention on finding out moment of inertia in different situations. And then once we are able to do that, we will see how moment of inertia plays a vital role when we discuss rotational mechanics. Right. So let's start by finding moment of inertia in different situations. So let's take the first example. Let's say we have a square such that there is a mass m placed at the four vertices, right? Now, this is a given arrangement, right? We have four masses, each of, let's take the masses to be equal. Let's say all of them have the mass m, right? And the wires or the rods that have been used to connect them, they are massless. So basically all the mass is with these point masses which are at the corners or the vertices of a square of side A. Right. Now, one very important thing I must say is that moment of inertia, let me denote it by MOI. So in short, I'm writing moment of inertia as MOI. So moment of inertia depends on axis of rotation. So axis of rotation, simply put, is the axis about which the body rotates. Now, this is again something the details of which we'll look at as we go along. Right now, let's simply understand axis of rotation as a line about which everything is rotating. Right. So in this case, there are three such possible orientations. So let me show them to you. If I draw the coordinate axis, this is the x-axis, this is the y-axis, and the z-axis is the axis which is coming out of the plane or into the plane of this board. Now, if you use the right-hand rule, you can see that x cross y gives you z. So z, the positive z, is pointing away from me towards you, that is out of the screen. So these are the respective axes. So since we have said that moment of inertia depends on axis of rotation, we can have three values for moment of inertia. So let me first write them as Ix, Iy and Iz. Now Ix is moment of inertia about x-axis, right? So when I write Ix is a moment of inertia about the x-axis. Similarly, Iy would be moment of inertia about y-axis and Iz would be moment of inertia about z-axis. Now to understand this, let me construct this square again. So these are the four pieces. Now first of all, this is the x-axis, right? So if I want to find out the rotation about x, the rotation would be such that this side would come behind and this would move outwards, and hence this kind of rotation would start. So this rotation that you see here is the rotation about the x-axis, right? Similarly, if we are to talk about rotation about y-axis, then this is the y-axis and the rotation would be something like this, right? So this is rotation about the y-axis. Once again, let's look at the z-axis, which is perpendicular. You see that when you rotate this about the z-axis, this is nothing but spinning this thing in its own plane, right? So you can get a feel of this by taking a notebook and rotating it by yourself. So let's once understand this using our own module. So this is a planar body. Once again, you can imagine an x-axis, a y-axis, and a z-axis which is perpendicular to this, right? So if I rotate it about the x-axis, the rotation would be such, right? Because this line passing through the middle is the x-axis and this book rotates about the x-axis, right? Next comes the y-axis, which is passing like this. So this must remain stationary at these points and then rotate like this, right? So this is rotation about the y-axis. The last axis is the z-axis, which passes through this, right? So for that rotation, the book would rotate something like this. So these are the three rotations about the x, y, and the z-axis. So let's now try to find the moment of inertia for all of these rotations, and we will see why these moment of inertias are different from each other. Right. So coming to the first rotation, when the rotation is about the x-axis, you see that the radius in which these four masses go is simply equal to half the side, right? Because when the square rotates, it will go in a circle of radius a by 2, as was seen in our example, right? In this rotation, you can clearly see that radius is equal to half the length of a side, right? So once we know that, we clearly see all four go in a symmetric motion and all of them are going in a radius of a by 2. So first of all, finding Ix, for Ix, we can say that Ix is equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus m4 r4 square, right? If we have four bodies, then we should have the summation of mi-ri square should expand like this, right? So four masses and four terms of mi-ri square. Now in our particular example, we have a symmetric situation, so I might as well write this as Ix is equal to 4 times mr square for any one body, which becomes m into a by 2 whole square. So when you square this term, a square becomes a square, 2n squared becomes 4, which cancels with this term. So Ix is nothing but m a square, right? So this is the moment of inertia of this body about the x-axis, right? Similarly, moving to the y-axis, you could for once argue directly by symmetry that x-axis is similar to the y-axis, so we should expect a similar result. To do that, once again, we should have four terms, m1 r1 square plus m2 r2 square plus m3 r3 square plus m4 r4 square. But since all of them are identical, we could say it is 4 times mr square for any one body. Once again, when the rotation happens along the y-axis, you see that the radius is equal to half the side of the square. So once again, you have a term like 4 into m into a by 2 whole square. So expanding this, you get 4 into m into a square by 4. The two 4's cancel and you're left with ma square. So this is the moment of inertia for rotation about y-axis, right? Moving on to the z-axis, Iz. Now when we have to come to Iz, we have to look at this rotation the rotation about the z-axis, right? So when that happens, you can see that radius is basically equal to half the diagonal, right? So let me show it to you on this diagram. If I draw the straight line, it will pass through the center, right? And when this goes in a circle, the circle is nothing but what I'm drawing right now, right? So it goes in a circle in its own plane, and the radius is equal to, if I call this O and this edge is A, then OA is the radius, which is half the length of diagonal. Now, if the side is A, then by Pythagoras theorem, we can say that this entire diagonal will have magnitude A root 2, right? It will be under root of A square plus A square, which gives you A root 2. So, half the diagonal would be A root 2 by 2, and A root 2 by 2 can be written as A by root 2, right? So this length OA is A divided by root 2, right? So once we get this value, the radius, we can once again say that since all the four bodies are identical, Iz is simply 4 times mr square for a single body, right? And that would become 4 times mass into A by root 2 whole square, where A by root 2 is nothing but the radius. So this becomes 4 into ma square by 2, and this gives you 2 ma square. So moment of inertia about the z-axis is 2 ma square. Now, we've gotten the three values of Ix, Iy and Iz. So what does this tell us? This tells us the inertia for rotation for all of these three axes, which means that the ease of rotation for x and y is the same, but this body would offer a higher inertia when you try to rotate it about the z-axis, right? So if you have such an arrangement where there are balls at the vertices of a square, there are two rotations which are exactly the same, and the third rotation is slightly difficult. So when I say difficult, what I mean is that rotation offers a higher inertia. And as we had studied in linear motion, higher the inertia, the more difficult it is to change the state of motion, right? So for your understanding, I'd leave you with these three animations which once again show you the rotation about the three axes.